An artificial intelligence just did a senior engineering team's week in one afternoon. At a company we call ACME, the model GLM 5.3 Flash built a complete load testing platform on a Kubernetes cluster, pushed a real web shop to its limits, and found where it breaks. This is what agentic engineering looks like. Dispatch. Here is the story in plain English. A company we will call ACME runs a web shop, and its engineers wanted to know one thing. How much load can the shop's read paths take before they break? Instead of doing it themselves, they handed the problem to GLM 5.3 Flash, running as an agent in a terminal. The model spent the session doing real platform engineering. It installed a load testing tool on the company's pre-prod Kubernetes cluster, wrote 6 test scenarios, ran a baseline, and then deliberately pushed the system toward its breaking point. And it did all of that without creating a single order and without ever touching production. Before we get to what it found, we need to answer a more basic question. What exactly is load testing, and why does it matter? Load testing means putting controlled, artificial traffic through a system to measure how it behaves under stress. And the craft has a ladder. You start with a smoke test, a tiny handful of requests, just to prove the plumbing works. Then a validation run, still small, to prove your measuring equipment is wired correctly. Only then comes the baseline, a few minutes of realistic traffic, which becomes the reference number every future test is compared against. And last, deliberately, the breakpoint test. You ramp the load up until something gives. Grafana's own documentation is blunt about why the order matters. No single test can uncover all issues, and each step on the ladder de-risks the next. On a shared environment like ACME's pre-prod cluster, skipping straight to the ramp would not just be sloppy, it would be rude. Real traffic runs through that cluster. That is the idea in one picture, a wave of simulated customers hitting the system all at once, on purpose. The weapon of choice is Grafana K6, one of the most popular open-source load testing tools in the world, with over 31,000 stars on GitHub. K6 is a Go engine you drive with JavaScript. You write a script that describes what a simulated user does, and the engine runs it thousands of times. 2 ideas carry the whole tool. Virtual users, the simulated people, each running your script in a loop. And the arrival rate, the dial that says how many requests per second should land on the system. You do not have to use both at once. The arrival rate is the honest one for breaking point tests, because requests keep arriving at your chosen pace no matter how far the system falls behind. And K6 separates observations from verdicts. Checks just record what happened, while thresholds are the pass or fail lines you draw in advance. Now, why run all of this on Kubernetes through an operator? Because of where the load comes from. A load test from an engineer's laptop has to squeeze through a tunnel, and it measures the tunnel as much as the target, about 100 milliseconds of network delay in ACME's case. The K6 operator flips this around. An operator is a Kubernetes pattern, a controller that watches a custom resource, here a test run, a 1-page description of the test, and makes the cluster match it. File the test run, and the operator splits your script across parallel runner pods that live inside the cluster itself on the same network as the shop. That hop measured 1.4 milliseconds. The load is real, synchronized, and representative, and because it is all declarative files, an AI agent can drive the entire thing end to end. One test run order. The initializer splits the script. Runner pods fire in cluster at 1.4 milliseconds. Here is where the session got interesting. The first validation run failed 3 times, and every failure was behavior that exists in no documentation. The custom resource was renamed Test Run, and every tutorial online still shows the old kind. The runner container runs as a non-root user, but the storage volume mounts as root-owned, so writing results failed until the agent overrode the security context. The operator mounts only the entry file, so multi-file scripts have to be merged into one self-contained file. And the cluster caches those files for about a minute, which means an instant rerun silently tests the old version. None of this is pattern matching from a tutorial. The agent read the actual resource schema from the cluster and worked from first principles, and then encoded every fix into its tooling so it never has to learn it twice. Before the results, a 60-second statistics lesson, because load test numbers are easy to misread. The average response time is the number everyone looks at and almost nobody should. Latency is long-tailed. Most requests are fast, and a few stragglers drag the mean while hiding from it. So the profession speaks in percentiles. The P50 is the median. Half the requests beat it. The P95 means 95 out of every 100 requests were at least that fast. It describes the worst experience a normal customer will notice. And this is why K6 separates checks from thresholds. A check just records, say, that a response was correct, and a failed check never stops the test. Thresholds are different. They are the pass or fail lines you set before the run, like P95 under 200 milliseconds. They turn a pile of measurements into a verdict. The baseline run, 5 minutes, 6 scenarios in parallel, about 12 requests per second of steady read traffic, 3,377 requests in total. Every single check passed. The P95 latencies, the search and product legs answered in around 75 milliseconds. The heavyweight 50-item search took 118. Even the slowest leg, the category listing, sat at 397 milliseconds, 5 times under its threshold. Beneath all of it, 31,725 rows of raw per-request data pulled off the cluster for analysis. That is what a healthy baseline looks like. Boring, green, and filed away as the reference every future change gets compared against. But the baseline also caught something the team already feared. A CME has a known filed defect. Under the right conditions, the business layer corrupts a fraction of responses, and the gateway masks the failure as something generic. A hotfix was active. In sequential tests that morning, the hotfix was perfect, 0 failures. Under parallel load, the counter ticked 20 times in 5 minutes. That is the quiet superpower of a dedicated counter. The defect stopped being a vague, flaky complaint and became a number per run, a number you can track and hand to the vendor until the real fix ships. The honest conclusion, a stopgap that passes sequential tests must be revalidated at the concurrency it will actually serve. Now the main event, the breaking point. The agent wrote a ramp from 2 to 38 requests per second in steps, nearly 8,000 requests per run, and ran it. 32% of requests failed, 4,500 server errors, the system fell over. A clean story, the API breaks past 30. Except the agent did something rare. It ran the identical ramp again, 30 minutes later, and this time 100% success, 0 errors, and latency actually improved as the load rose. 2 opposite outcomes from the same script on the same morning. Some days the road holds. Some days it simply is not there. So, verdict. The claim everyone wants, the system breaks at exactly this many requests per second, is not what the evidence shows. 2 identical ramps with opposite outcomes refute any clean limit. What ACME actually has is a nondeterministic stability cliff. Most days the path sails past loads it was never rated for, and some days it falls over entirely. That reframes the whole risk model. The danger is not that too much traffic makes the shop slow. It is that the path can collapse without warning. And notice the discipline here. The easy story was the collapse run. The agent ran it again, got the opposite, and delivered the less satisfying, more honest answer. One run proves nothing. The follow-up is already queued. Repeat the ramps to measure how often the cliff appears. Then push on toward 80 requests per second. One more thing, because it matters as much as the numbers. This was an autonomous agent operating against a shared, live test environment, and at every step it behaved. Order placement sat behind a gate that required an explicit flag and human confirmation, and the agent refused to cross it. Every shopping cart a test created was deleted in a cleanup block that runs even when the test fails. Default load stayed well under the documented throttles. Soak tests were capped at 5 minutes out of courtesy to real traffic, and production clusters stayed read-only the entire time. Capability without discipline is a liability. This session was both capable and disciplined, and that combination is the actual headline. If you want the next story about AI agents doing real engineering before it becomes a case study, subscribe to AI Security Dispatch. We follow the receipts. See you in the next briefing.